So we're talking about the diffraction grating and how similar it is to the double slit experiment. In the double slit experiment, we had monochromatic light, so you can show these wave fronts coming like this. So you guys now know Huygens principle. Huygens principle says that each point on a wavefront acts as a point source, and you can draw an infinite number of these point sources. Each point acts as a point source for what we call wavelets. So you get these wavelets like this, like this, like this, and then the new wavefront is going to be tangent to those wavelets like that. Okay, now what happens when this wavefront here strikes this boundary? So this wavefront comes in like that, like bam, like this. This wavefront comes in. So you put a little point source like this. What's going to happen to the wavelet from that point source? It's going to get blocked, right? It gets blocked right there. How about a point source that was like right here? It's going to get blocked. But you do have a point source right at this opening, and you get these wave fronts that move out like that from both slits, right? Kind of like this, these wave fronts that move out, and then you get this interference pattern, like right here would be constructive, constructive, right? And the pattern that this gives is it's called an interference pattern. Bright, dark, bright, dark, bright, dark. A better view of this is this one here from yesterday. So this is a really nice view of it. So you have this wavefront that comes in, hits the opening. So you got a point source here, a point source there, and then you got constructive interference like this, leading all the way to a bright spot. Okay? Now, let me see if I can go back. Oops. Okay, so a diffraction grating is remarkably similar to the double slit experiment. But what it is it's a lot of slits. So instead of just having two openings, you're going to have a lot of openings. You're going to have slit, 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 slit. And all of these slits are the same distance apart. Okay? So they're all equidistant. So the distance from that slit to that slit is D. The distance from this slit down to this slit is D. Right? They're all the same distance apart, moving downward. Now, what happens when light strikes a diffraction grating? Oh, and just to give you an idea of how many slits are here, the diffraction grating I have right here in my hand has 1,000 gratings per millimeter. 1,000 gratings. There's 1,000 marks per millimeter. So there's a lot of slits on here. So when you have a wavefront, when you have light ray that comes in like this and strikes, we're going to get an interference pattern over on the screen. In fact, let me show, before we talk anymore, let me just show you in real life what you get. So here is a diffraction grating. I'm going to shoot a laser through it. Now a laser is a type of monochromatic radiation. So like this is a blue laser, but I also have a red laser, and we'll look at the difference between the two. So I'm going to shoot a laser beam through the diffraction grating, and you look up at the wall. Hold on. All right, let's see. Hold on. I got to turn it the right way. There it is.
Whoa.
Okay.
Whoa.
Now, tomorrow, I ordered, so I saw this once. I ordered online. It's called Magic Fog. It's like they use it for movie sets. It makes it real foggy. So tomorrow I'll do the same thing, but I'll spray the Magic Fog, and you can actually see the laser beams diffracting from the diffraction grating. Okay, but the thing I want you to notice is that the points up on the wall are it reflecting off?
Yeah.
It's reflecting behind me?
Yeah.
Oh, it's
almost in your eye.
Like that?
You're good.
But here's the thing I want you to notice. When you work with the diffraction grating, you're going to get these points that are like this. Very, very distinct marks. Now, with the double slit experiment, it was not like this. with the double slit experiment, when you looked at the screen, so over here, this was the screen for the double slit. So I'm just going to draw a sketch of the double slit. So here was the double slit, right? The pattern we got with the double slit looked like this. So we had a big bright spot kind of in the middle like this, and then went to dark, and then this kind of tapers down like this, and then the intensity gets less. So what these bumps are showing is the intensity of the light. The bigger the bump, the more intense it is. Now with the diffraction grating, the intensity goes like this. And this is what we have to talk about. The intensity is like, at this point right here, you get these points up on the wall. The intensity is like, boom. Very sharp. In fact, probably even sharper than that. Let me try again. It's going to be like this. This big, sharp thing. And then it goes flat, 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 flat. And then boom, like this. Like that. And then flat, 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 flat. Boom. Yo. Oh, thanks. Okay, then the same thing the other way. Flat, 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 like little intensity, little, very small, and then boom, very pronounced intensities. Okay? Now, what's the difference here? Why do we get such pronounced marks with the diffraction grating? Oh, yo.
I think I know why.
Why? Well, hold on, let me finish
Okay.
though. Whereas over here, what we have is the double slit. So with the double slit, like look, we have this big fat bright region, okay, and then here it's kind of like a gray area. See how like the intensity kind of gets bigger? It's not like super confined to one point. We have this gray area. This would be the most intense, then less intense, less intense. There's the minimum right there. Then more intense, maximum intense. You know, it's kind of like this pattern where, you know, you have degrees of constructive interference. What were you going to say?
Oh, never mind. Keep going.
Okay, so here's what happens in the double slit experiment. Look, so let's just pick this the first order bright right here. So here's the first order bright. You have light rays that are traveling from the two slits. You have a light ray that goes like that, then you have a light ray that goes like that. Now, that point right here is where the interference is going to be maximum constructive. When the waves reach the screen, they're totally in phase. But what if you look at a point that's slightly off of there? What if you look at a point that's like right here? So it's not totally at the peak where you're getting maximum constructive interference. Well, so here, so we're going a little bit farther up. Is it still constructive? A little bit. Would that still be considered constructive? Is it all the way to the minimum? Is this point right here all the way at a minimum? No, so it's kind of constructive, kind of destructive. You get these gray areas, right? Now, with the diffraction grating, it's all or nothing. Okay, you get these very, very pronounced points. So let's look at why. So the reason why. So let's focus in on this point right here. So you have these rays that are going from, let's do like this. So you got a ray that goes to that point, and then you got a ray that goes to that point. So the same logic applies. Let's call the top ray ray 1, the bottom ray is ray 2. Which ray is traveling farther to get to that point? Ray 2. So you go like this, just like we did with the double slit experiment. You drop this down like this. This extra distance traveled, we'll call it delta x. The extra distance traveled is equal to d sine theta, where what theta is, it's the angle inside here. It's the angle inside that little triangle right there, but it's also the angle from the midpoint between the slits up to the point you're focusing on, like that. It's also the angle from, you know, the deviation of the ray. Now, let's keep going. Now, what has to be true in order for ray 1 and ray 2 to interfere constructively right here? What has to be true about this extra distance traveled for this to be constructive and to be real bright? The extra distance traveled by ray 2 has to be equal to what? 1 wavelength. right? Exactly one wavelength, and if that's true, the two rays will meet in phase. Okay, well, let's look at a ray that comes from right below. So let's go to the next slit down. So the next slit down, I'm going to draw in ray 3. So ray 3 comes from this slit up to that same point. Now, if these slits are the same distance apart, so there to there was D, and then there to there is 2D, what is going to be true about this extra distance traveled? It's going to be equal to exactly 2 wavelengths, right? Which means, because if this right here was 1 wavelength, we basically doubled the hypotenuse of that little triangle. So if this is D right here, then here to there is 2D, which means that this would be 2 wavelengths. Okay, so let's keep going. Let's draw another ray from the next slit down. So you go to the next slit down right here, draw a ray like that, bring this down here. What's going to be true about this extra distance traveled? If this is 1 wavelength right there, this is 2 wavelengths, this is going to be what? 3 wavelengths, right? So all these rays are meeting constructively right at that point. That makes sense? So you get this really pronounced bright spot. Now, what happens if you're just slightly off that bright spot? If you're slightly off the bright spot, erase all this. So let's say we're looking at a point that is just slightly above this bright spot. We're going to look like right here. And again, we'll look at 2 rays. So boom, we have a ray going like that. Then we have a ray going like that. So let's say that this extra distance traveled, let's just say that this is like 1.1 wavelengths. This is what the guy on Khan Academy did. I like his approach. Way better than what the textbook, how the textbook explains it. So if that's just like 1.1 wavelengths off, well, is that enough to give that much destructive interference? If you're only off, you know, here's a wave, right? So what we're saying is, if we're comparing these two, so here's one wave, okay, so this is like, this is this guy, and then the next wave hits, so 1.1 would be like here, right? With down here would be 1.5, that's 1.5 wavelengths. So 1.1 is right there. Well, dudes, why would that give us destructive interference? You know what I'm saying? Shouldn't that be a gray area? Shouldn't it kind of like be, you know, not fully intense, but a little less intense? You know what I'm saying? Okay, well, let's keep going. Let's go to the next slit. So you go to the next slit down, go to that same point. Well, how off is this guy going to be? If this guy's off 1.1, this guy's going to be off what? 2.2. So, you know, 2.2, so that's going to be, so that he's going to be like, it's going to be a point like right here, something like that. So a little less. Let's keep going. Down like this. This guy's going to be off how far? 3.3. How far off is the next guy going to be? 4.4. How far off is the next guy going to be? 4. Oh, dude, so now we have a ray that's off by half of a wavelength. So what's going to happen to this ray and this ray? A 0.1 and a 0.5, that's pretty much going to be, huh? Oh, 5.5.
Yeah.
Oh yeah, thanks. 5.5 wavelengths. But what really matters, you know, the 5 doesn't matter, the 4 doesn't matter, the 3, what matters is the points, like, because it's what phase you are on the waves. Like right here's 1.1, 1.2, 1.3, 1.4, 1.5. So look, this point right here, a wave that hits at that phase is going to pretty much cancel with a wave that hits at that phase. So even though the first 2 rays right up here, even though these first 2 rays, you're like, well, that's not totally destructive, but you know what is destructive? This ray with this ray, right? Because here you have like a wavelength, and then here this is at that's at wavelength over 2, right? So this ray up here is going to totally cancel with this ray, whoa, down there. Which is why you get these super pronounced peaks like this, where everything else in between cancels. So the equation for diffraction grating, it's still the same equation. When you're working with diffraction grating, you're still saying that d sine theta is going to be equal to m lambda, where m can be 0, 1, 2, you know, and so on like that, for constructive interference, where d sine theta is the extra distance traveled. And then you can also use this equation, y, which is where the bright spot is on the screen, equals m lambda L over D. Wait, did I write that down correctly? Those were the equations we derived for the double slit experiment. Yeah, that's right.